This project has evolved a lot since I first submitted the abstract, and now it's geared more toward a study of how behavior affects the movement characteristics of large whales and the different scales at which patterns emerge. Movement is the catalyst of ecological processes from the individual level to the population and community level, and the characteristics and drivers of movement can vary at different spatial or temporal scales. Ecological processes are often hierarchical in nature, where each order is informed by higher-level orders. For example, the selection of a geographic range is dependent on the selection of an individual home range, which is dependent on other higher-level processes. This concept can also be visualized on spatial and temporal scales, where smaller, more local-scale processes, like selection of a feeding site, inform processes at larger scales, like selection of a home range. And this concept of hierarchical orders can also be applied to animal movement, as longer periods of movement are made up of a series of shorter duration movements, which may be driven by different processes, like how seasonal migrations can be driven by the timing of seasonal increases in productivity, while daily movements are related to more local variations in prey density. So I wanted to see if there were different scales at which large whale movement behavior seemed to organize, and if we could identify any behavioral drivers of that movement. As most of us probably know, studying whales is challenging because the time they spend underwater limits opportunities for observation. So biologging methods are often used to collect data remotely, but the challenges of keeping a biologger attached limits the type and scale of data that we can collect. The movements of large whales are typically studied using tracking devices that can monitor the whale's location over periods of months or even up to a year, but the spatial resolution of the data are often relatively coarse, and there's often no behavior data associated with the tracks. Much of what we know about large whale feeding behavior comes from suction cup archival tags, which record things like depth, body orientation, and sound production at very high temporal resolutions. This figure on the right shows an example dive profile from one of these tags. And these tags are great for looking at behavior at local scales, which is maybe less than 10 kilometers, but the relatively short attachment duration makes it hard to link that behavior to larger scales. More recently, intermediate or medium duration archival tags have been developed that can continuously record behavior data over periods of multiple weeks, providing access to movement and behavior data at a range of scales, and allowing us to start looking at linkages of local scale processes to broader scale ecological patterns. I used data from 8 intermediate duration archival tags deployed on blue whales off Southern California during July and August of 2014 and 15. The tags stayed attached for about 3 weeks while continuously collecting depth and accelerometer data at 1 Hertz and fast-locked GPS locations, which worked out in most cases to a location about every 15 to 30 minutes after accounting for poor quality locations. Feeding lunges were identified from the accelerometer data using automatic detection algorithm implemented in MATLAB. Now, the relatively long attachment duration, continuous record of dive behavior, and frequent locations allows us to investigate movement and its associated behaviors at different scales. To do this, I conducted a series of analyses of the tracks to identify the number of latent movement-based behavior states and the scales at which they occur using hidden Markov models implemented in the R package Momentum. This method first fits a continuous time movement model to the tracking data to predict locations at regular time intervals and calculate movement metrics like step length and turning angle. The regularized tracks are then fitted to a hidden Markov model to identify latent behavior states based on the movement characteristics of the tracks. To investigate how movement behavior changes across scales, I needed to vary the grain size, or the minimum unit of the analysis, and look for places where the trend changed rapidly or became less deterministic, which can indicate a transition from one scale domain to another. So I repeatedly fit the same tracking data with both 2- and 3-state hidden Markov models using time steps ranging from 1 hour to 36 hours, and then compared the AIC between the 2- and 3-state models for each time step. The results showed a general trend of declining AIC with increasing location time interval, shown here on the left panel. But what was interesting was how the AIC difference between the 2- and 3-state models changed with increasing time step, and the difference is shown here on the right. The three-state model is favored at short time intervals, where lower AIC equals better model performance. But as the time step increased, the difference between the two models declined and became very irregular at around the 12 to 14 hour time step. So this suggests that the three-state model describes tracks better at the fine scales, but the two-state model performs equivalently at broader scales. So to dig in a little deeper, I looked specifically at the model output of the 1 and 12-hour time step models. These figures show the distribution of step lengths on the left and turning angles on the right from the tracks. The three latent states identified by the 1 hour time step model consisted of a linear state with long step lengths and small turning angles, an intermediate state with shorter step lengths and somewhat wider turning angles, and a clustered state with short step lengths and a very broad distribution of turning angles. The two-state model at the 12-hour time step was characterized by a similar divide between a linear movement state with long step lengths and relatively small turning angles, and a clustered movement state with shorter step lengths and a broad turning angle distribution. It's interesting to note how the overall distribution of step lengths and turning angles, the gray bars in the back, changes with scale. And the step lengths for the 12-hour time step are skewed more to the left, and the turning angle distribution is broader with greater density at the extremes compared to the 1 hour time step. Remember, this is the same tracking data, just aggregated at different temporal scales. So HMMs allow the inclusion of covariates to test their effects on model estimated parameters like the transition probability matrix, so we can look at the behavioral drivers of different states. As clustered movements are often assumed to represent foraging, I tested the effect of feeding rate, here summarized as the number of feeding lunges per hour during a time step, on the probability of being in each state. We see that the whales were most likely to be in the clustered movement type at high feeding rates, where linear movement type is the least likely. This indicates that feeding most often occurs during clustered movement types, but the higher probabilities of the intermediate state compared to the linear one indicates that it might represent short duration foraging bouts or maybe some sort of exploratory movements. Looking at the two-state model, at the broader scale, 12-hour time step, we see a similar trend with clustered movement state being more likely at higher feeding rates, but the confidence intervals are wider than the 1 hour time step model, and there's a greater chance of linear classification at low to intermediate levels of feeding, suggesting a reduced contrast between the two states. I don't have time to go into it here, but the continuous dive behavior data from these tags offers an opportunity to examine other possible behavior drivers of these movement states as well. So the work presented here is an attempt to link local scale behavior to broader, more regional scale trends and ecological patterns. The goal is to use these rich but still temporally limited data to inform broader scale trends in observed in sparser data, like what researchers might have when using location-only tags over long time periods. It also will provide a basis for better interpretation of patterns identified by more recently developed long-duration tags, which are beginning to collect summarized dive behavior in addition to movement data, but remain limited in the amount of data that can be recovered and susceptible to data gaps. And with that, I'm about out of time, so I'd like to thank all the people who made this work possible and acknowledge the permit and our funding folks. Thank you very much.